Hello everybody, welcome back to this studies for electrical trades review. We stopped last time at the molecule. We said molecule was the smallest particle or parts of a compound. If you break down water, if you still have a drip of water, that smallest drip is still called a compound. Still called a molecule of water, which can, if they break it down between oxygen and hydrogen, that's not molecule no more, that become atoms itself. Today we'll talk about the electrical quantities such as coulomb, amp or ampere, volt, ohm, and watt. What is a coulomb? Coulomb is a quantity measurement of electrons. It's a quantity measurement of electron, and 1 coulomb is equal to 6.25 times 10 to the 18 electron. That's how many electron 1 coulomb has. We will discuss these things with further detail maybe in next few classes. Let's go to the amp or ampere. Ampere is defined as 1 coulomb per second. So if you have a 1 coulomb per second is called amp. So, or we can say that 6.25 times 10 to the 18 electron over 1 second travel is equal to amp. Okay, so that is there. And what is volt? Volt is an electrical quantity too, and the definition of volt will be the amount of potential require or to cause required to cause 1 coulomb to produce 1 joule work. One joule work. So that is a volt. Volt is generally defined the amount of potential required to cause 1 coulomb to produce 1 joule of work. Resistance is defined. Ohm is defined as resistance that can control the flow of current. Control the flow of current in a circuit. Okay, so that is our, and it also has another function, that is the voltage dividing. So resistance has a resistor or resistance, or ohm has a, ohm is it's named after a scientist name, chemist, or whoever invented that ohm. But resistance has 2 main jobs. One is the control of flow current in the circuit. The other one is for the voltage dividing. Now we said the watt. What is watt? It is also electrical quantity. The amount of power used in a circuit. This is a power. That's a unit of power. This is a resistance of unit of resistance. Volt is volt, potential energy, or we can call it a electromotive force too. Okay, so what is what? The amount of power power need for a circuit. Okay, so we got these base. We probably have to come back to these things with the detail. And now let's move on to electron theory. Electron theory, what is that says? It says that the current flows from the most negative to the most positive. The current we said amp, current unit is amperage, amp, flow from the most negative to the most positive terminal. Okay, so that is a electron theory. The electron theory states again, the current or the amperage flows from the most negative to the most positive terminal. Now there is another theory about that. It's a conventional theory, which is the opposite of the electron theory. It says that that the current flows from the most positive to the most negative. The current flows from the most positive to the most negative. Alrighty, so which one is right then? The question is, we have two theories, and which one are we using in a daily life? Let's see if you guys can think of an answer here. Pause that video and think about it for 15 seconds. Alrighty, so we still up until today, I use a conventional current theory too, and all the skill trade people use a conventional current theory, and the engineers follow the conventional current theory so far that I've seen. There are reasons for that. There is one reason, because we usually, the negative terminal, we tie that to the ground, to the common side, or grounded, so that will leave positive to be above the ground. And the second one is most people think that plus is hot side, and so negative is common. or neutral. So these are a couple reasons, and we also have another reason, which will be because on the schematic prints, on the schematics, in the right, on the left top side is the supply voltage. In the bottom right side, it's connected to the ground. The ground symbol is usually like that. So, and that's the third reason they use it, like from left top is the supply and the bottom right is the ground, and that's why they use a conventional, because they go from the hot side to the neutral side, or the plus side to the negative side. Since we got that clear, let's move on to the speed of current. We said current is it's using a electron that we talked about the last session of the lecture. It has to be a lot of electrons to make a current. That will be the valence shell movement, and there will be many elements to do it, because the current or the impulse of electricity is actually fast, but the electrons are moving very slow. That's being said because there has to be billions of electrons to move, and that's exactly what's happening. Since we said the Coulomb has a 6.25 times 10 to the 18, 6.25 times 10 to the 18 electron. Let's say like if you have like 15 coulombs moving through a wire, so that requires, what happened is there, even with a slow moving electron, when they try to enter the wire, electron going into the wire, some of them enter the wire, the other has to leave, and that's what caused the speed of the impulse here, because one is coming, another is leaving. So that's the speed of current right there. Now let's go up to the basic electric circuit. In order to make a circuit, complete circuit, for the current to flow, we should have a complete path. Complete path means we have to start from a terminal, go all the way around, come back to the other side of this terminal. If it's a battery, power supply, or anything. So this is a complete path should be required, or it is required, or it must be required to have a current flowing through a circuit. If not, it will not work. For example, if I push this button, turn that on, so it will close this circuit right here. It will be like that. If it closes, it will be flowing the current from here going there. If it is 120 volt, for example, this current will flow from here. Then let's say the amp is 0.5 amp. The 0.5 amp is now closed. It's lighting up this light bulb, and we'll just complete the circuit. The moment I break the circuit, there will be no more current going through that, and this light will go off. So now let's since we talked about circuit, now let's say short circuit. So this was a complete circuit, this is a short circuit right there. Let's see what short circuit is. Short circuit occurs when there is a little to no resistance to control the flow of electron. So what is that saying? I have a battery here connected to this light bulb, same exact circuit, but if there is a wire or a bare wire going from here to there directly, it doesn't matter if I close the switch or not closing that switch, the electron or the electricity will find the shortest way back, which will be this way back. If that happens, it will create a whole there is no resistance to it, because this will be our resistance as using it. So the whole resistance, it will just short the circuit. It will not light up this bulb. So there is the short circuit here. Because if we close this thing or not closing this thing, it's already closed by this wire. So the current is flowing back. It's coming from this direction back to here. And for example, it's here too. So we got a short circuit is like, short circuit will be, for example, it's connected right here too. So there's a string coming out of this wire, or this wire is touching this wire right here and this wire here. So this battery was designed to only supply this light here. Now it's only not supplying this light. It's going back to the source. When the conductor is leading from and going back is connected together, that's what causes shorts. So this is leading and going back, they are both connected. Going back is this terminal, and this connected to the source back, that will cause short. Again, the leading coming in current conductor way, and going in back or going back, which is this way, is connected back to this incoming wire or the incoming conductor. They're all connected together. That will cause a short circuit. And that if there has a breaker there, it will trip a breaker, because it's no resistance is going, because it's bypassing that, because electricity will find its shortest circuit, its shortest way to go back, and that will be this way. This will ignore right now. Or if it even has, it will be having a little light, not more. Okay, so the short circuit. Now talk about the ground circuit. What is a ground circuit? Ground circuit, it occurs when the current flows on a route other than intended to. What does that mean? For example, we usually use power for the AC. For example, if you're wiring a 3-prong switch, 120 volt AC, and we have a neutral, this will be plus and this will be negative. So these are, okay, let's say for example we got this. So we defined a ground circuit is it occurs only when the current flows in a different route than it was originally intended to. So we got power coming into this, for example, a 3-prong switch here. So this one, right here, ground, plus, minus. So this will complete the circuit here. But if something happened, there is something equipment device failure, but now this is our returning route. This is usually connected to the grounding terminal there in the machine or on the equipment itself. Since we have 120 going in and this should be coming back and making a complete circuit, but now the route is this plus that. We have two routes because it's grounded to the machine. The current is flowing through this way too. It will be excess of current there. That will cause excess, not excess, but excess of current. And in that case, if we have a fuse or a circuit breaker, fuse will blow or circuit breaker will trip. It's a good protection, the grounded circuit. The ground terminal should be always there to protect a hazard situation. For safety reason we use it. Ground wire in a machine, or even in the three-way prong that we have in our house. 3 prongs. One is hot, one is neutral, one is grounded. Never ever cut that third wire, which is the ground, from any machine, equipment, or simple receptacle. Now we did define the voltage. Now let's go and talk about again. Volt, it is also called electromotive force or EMF. Again, a volt is the amount of potential required to produce 1 joule of work. We said that earlier too. Now how we define it like this way. This is the definition by just a formula. A potential energy is required to produce 1 joule of work. 1 joule of work right there. A joule is the unit of work. So the joule over coulomb is defined as a volt too. Or we can say volt is equal to I time R. I is intensity of amperage. Intensity of the current, I'm sorry. And R is resistance. R is resistance right there. So that's how we can define the voltage to I time R. I is the intensity of the current, or the amperage. R ohms is measured in ohms, so resistance is measured in ohms. So this is how we define it also. Now I have a note here. So people have a lot of misunderstanding here that volt can flow from a wire. So I have up to 20 volts. I can do anything. No, the voltage is just a driving force. It just pushes the current through a wire. Voltage does not get pushed through a wire. It just pushes the current through a wire. It's like pressure in the water pipe. Pressure cannot go in a pipe. Pressure pushes the water, and water moves, water flows. So it's same terminology there. Now, what is Watt? Watt is named after James Watt. It was a guy that tried to sell the steam engines, and he was the one that he found the watt, and he found the unit of power, which is watt. And watt is not the only unit power that we use today. We have a horsepower that we use. We have a British thermal unit, we use that. And there are some joule, calories, and everything that we use for the power. So let's define it. Amount of power that is being used in the circuit called wattage, or watt, simply. This is a genuine formula for watt, and where P is power, V is a voltage or electromotive force, and I is current or amperage. This can be written in a very different. Okay, so we can also say that in here we have an I right there. If I get we got I there, but V is equal to I time R, right? So we can use this and substitute it here. Will be I time R time I. That will become I squared time R. That is the third formula for watt or power. So we can use either of these to compute the watt of, or the power of a circuit. What is a horsepower? Horsepower, James Watt was trying to sell his steam engine, and he has to do something with a common math that every individual can understand what he did. So he tried to experiment a lot of work through horses, and he found that a horse can do 550 foot-pound work in a second, and that's what he called that. That's how we call that as a horsepower, because that can be achieved in 1 second by this statistics. So how is that in a minute actually? So basically you have a 1 second that will be timed by 60, because 1 second is equal to 1 over 60 minute. So if you flip that, there will be 550 times 60, which will give us 33 some thousand. No, which will 550 times 30, times 60 will give us 33,000 foot-pound per minute. Okay, now let's move on. For the example, so for example, I forgot the foot-pound. What is foot-pound? Amount of force required to raise the 1 pound weight 1 foot. That's what we call a foot-pound. A foot-pound amount of force required to raise 1 pound weight 1 foot. This rate is called a horsepower. Let's move on to example here. An electric car, let's say Tesla, pulls or tow 3,500 towing capacity for 500 miles in 5 hours. How much horsepower does this Tesla have? So let's work on that, because we have a lot of formula to work with these things. To compute a horsepower, we will use this formula right here. So we have so we created this formula for the horsepower: 3,500 pounds times 500 miles, which 1 mile is equal to 5,280 foot. And we divide that by 5 hours, which 1 hour is equal to 3,600 seconds or 1 hour. So we will cancel these things out and do the math, use the calculator. We will get 5,133,333 horsepower. The Ohm's law states that it takes 1 volt to push 1 amp through 1 ohm resistor. So it takes 1 volt to push 1 amp through 1 ohm resistor. The Ohm's law the resistors or ohms is used to measure electric resistance, and there is one more use for that, is voltage dividing. What is that being said is like that. We have a circuit here, for example. This is a battery, 1 resistor, 2 resistor, 3 resistor. So we got 2 resistor, for example. So we got a voltage supply there. We get a volt. So we got this one, a V1. So voltage 1 right here, voltage 2 right here. So there's a 1 drop right here, the second drop right here. So we have 2 different drops. So that's the job of resistor too. This cannot be only resistor, a light bulb, a horn, a buzzer, anything that have a resistance to it. We can just say like, okay, that is a job of a resistor or Ohm's law, to do a voltage drop, divide the voltage there, and control the flow. It's also controlling the flow here in resistors. That's 2 jobs that resistor has. Let's move on to example here. A vacuum cleaner is connected to 120 volt AC source. It has a current rating of 3.5 amp. What is the resistance? We say this was a resistance formula right here. This is the same thing. You can write it down as I times R. You can find for I will be V over R. Okay, so now we need to find this guy. Voltage is given, so V is equal to 120 volt AC. We don't usually write AC, but let's write it down. And the current rating is 3.5 amp. and resistance is unknown. So let's find for resistance. So it's given already here. R is equal to V over I, or voltage divided by current, 120 volt divided by 3.5 amp. 120 divided by 3.5, 34. So R is equal to 34.3 ohm. Example 2. A vacuum cleaner has a 0.5 amp current rating or half amp rating. It is connected internally to 480 ohm. What is the voltage supply? So let's see. We need to find a V. V is equal to, we can use this guy. V is equal to I time R. I is given, amperage is given 0.5 amp. Time R is 480 volts. 480 ohm. So V will be equal, half of 480 is 240 volts. So 240, for example, not used in USA. It might be in Europe. Or Asian country. Because they use 220 volt that I know, they might handle 242. So that's how we find it. Now let's do the last example, hopefully. An elevator at Burj Khalifa can lift load of 10,000 pound, and it covers 504 meters, which is 1654 feet, and this is done only in 60 seconds. How much horsepower that has? There's a quite of example right here. So 1,000 pound. We did the same example with a Tesla there. 10,000 pound. The good thing is we already calculated that 6 times 1654 feet, and it's done in 60 seconds. I can tell you that it will be a big motor according to the horsepower will be. So this 0 will go with this 0. Now let's do some math here. 1,000 times 1654 divided by 6. That is a big motor. 275,666 horsepower motor. Yes, it technically it does make sense because 10,000 pound, and it goes to this height, which will multiply by itself by the weight capacity, and it goes only in 60 seconds. So that will require a big motor, like a really big motor, which will have a big horsepower to go and take it that high speed and the load capacity. Keep in mind that. Okay, so I think we exceeded our time limit here. We will talk about the resistors and resistor band, the color bands, and maybe we will cover just a little bit of metric system next time. So please don't forget to hit that like button and subscribe this channel. And until next time, take care. See you.